All right, so now we are going to go back to week 7 notes to section 3.8. Section 3.8 is about this idea of a differential. You can intuitively think of a differential as being a sort of error measurement almost. Going back to what the definition of the limit is, of derivative. We have the limit definition, limit as delta x goes to 0 of f of x plus delta x minus f of y, or f of x divided by delta x. Well, if we think about this thing, dy dx, could also be rewritten as the limit as delta x goes to 0 of dy, of delta y over delta x. So we're really saying when this change in x gets really small, and in that way, when we have, this is the derivative of f(x), we have something like f prime of x, and we multiply it by dx. This is like dy. Technically, we can't entirely say this. If we're being pedantic about this, we have to say we have to unimpose the limit, rearrange our terms, reimpose the limit. But we're not going to get into all of that because I'm not going to be overly pedantic about it. Having said that, we can think of f prime times the differential dx as being equal to the differential in y. Okay, what does this mean? Let's think back to what's happening here. dx, that's really just like what happens to delta x when you let it go to 0, when it gets really small. So in some sense, we can think of dx as being similar to the limit as delta x goes to 0 of delta x. It's not that. Notice I didn't write that they're equal because it's not equal. It's not entirely the same. This is actually called an infinitesimal, and there's a lot of non-standard analysis that goes behind all of this that we're not even going to touch because that's graduate level stuff. What I'm going to say is this thing is kind of like this, kind of. So what we're saying here is that if you take the derivative of a function and you multiply it by a small change in x, change that's close to 0, it's going to give you a decent approximation for how y changes when x changes close to 0. Not exactly the same, but close. And in the same way that this dx can be thought of as analogous to this limit definition, this can be thought of as analogous to delta y. These are not the same things. I have to be clear here. dy and delta y are not the same things. dx and the limit as delta x goes to 0 of delta x. These are not the same things. They're analogous, not the same. dy is a differential, dx is a differential, and they represent the infinitesimal changes in x and y. What delta x represents and delta y represent are non-infinitesimal changes, so changes that you can actually measure. So maybe delta x is 0.1. Maybe delta y is 2, whatever. dx, dy are not the same thing as delta x, delta y. But again, we have these analogous type definitions, or descriptions rather. So what's happening then is that as this definition would hint, the change in y is equal to f of x plus delta x minus f of x. And again, the change in x is just the change in x, right? What this is telling us, this idea of the differential is telling us, is that for good approximations of changes in y, it is enough to say, so if you want to approximate dy, this is close to delta x times f prime of x. It's close. It's not the same. It's close. They're approximately equivalent. And the smaller that delta x is, the more accurate this dy measurement is. What this dy measurement is telling you is exactly how high the slope of your tangent line goes with small changes in x. In other words, zooming in on our function, if you take and apply a very small delta x, our function doesn't change that much in height compared to the tangent line. Here we'll see that we can't distinguish the two, right? They look exactly the same. It's not until we move a little bit further over that we can even start distinguishing the two from each other. And that's what this dy, delta y, dx, delta x idea is trying to tell us. We can think of this as error measurements. How accurate or how close is our tangent line to our function given some change in x? And we can find out by comparing the way dy and dx behave to delta x, delta y. Is that cool with everyone? Folks at home, does this make sense? All right, I'm going to assume the quiet stoicism is a yes. Again, this is really just all about error estimates, error measurements. That's really what we're going to be talking about here. So we're going to assume that dx is 0.01. Let me write some of this out now. Yeah. All right. Let me write some of this out to make sense of everything. dy is equal to dx f prime of x. Delta y is equal to f of x plus delta x minus f of x. This tells us how, for infinitesimal changes in x, y changes, and this tells us how, for changes in x, y changes. So this is what our function does, this is what our tangent line does. Cool? Okay. Now, in our problem, we're told that our function f of x is equal to x squared. We're told that x is equal to 1, dx is equal to 0.01, so 10 to the negative second, and that we're going to look at delta x on the same scale. So looking at how our tangent line changes, dy is equal to dx times f prime of x. Well, this is going to be 10 to the negative second times f prime of x, f of x being x squared, so f prime of x is going to be 2x. And at x equal to 1, we're going to have that dy is equal to 10 to the negative second times 2, or 0.02. Agreed? So this is how tangent line changes in y. Now, looking at delta y, well, delta y is equal to f of x plus delta x minus f of x. So this is going to be equal to 1 plus 10 to the negative second minus 1, right? Well, this is going to be equal to 1.0002, I think. Let's check. Getting out my calculator really quick. Yep, 0.0201. Let's get back to that. 0.0201 minus 1 is equal to 0.0201 is equal to the change in y. So what this is telling us is that on the scale of changes, when we change in our x-axis by about 0.01, so that's not the same function. Here we go. When we change, this is the graph of x squared in black, and this is the tangent line in gray. When we move over from x equal to 1 by about 0.01, the difference between our function and the tangent line, it only differs by about 0.0201. My mistake, it differs by about 0.0001 is what I mean to say. So there's really not a huge difference between our tangent line and our function. This is what we're trying to say here. Does that make sense to everyone? Folks at home, does that make sense? I think I lost the folks at home. All right, well, because of these small changes in y, we can say for small changes in x, our tangent line is a pretty good approximation to our function. Does that make sense? That's really what this is. This whole idea of the differential and of these delta x, delta y, they're really just measuring the error. How far off is your tangent line from your function? For my engineering students, this actually is going to show up every now and then whenever you measure things like tolerance. For my physics students, this shows up whenever you have error measurements, same for chemistry and biology. Whenever you're talking about instrumentation and it has an accuracy of whatever, you have to go through these differential methods to find out how accurate the final measurement actually is. And that's based on the error in several different tools across the entire experiment. So having said all of that, let's see an example. Well, first, just like this says, we're noticing that for small changes in x, dy and delta y are about the same. So our tangent line is a decent approximation for our function in those ranges. Before we get into marginal analysis, do I have, yes, I do. Okay, this is a great example of what I'm talking about, error propagation and where this gets used in the physical world. Here we've got a caliper that's measuring the radius of a sphere, or I mean the diameter of a sphere. And in doing so, it gives us the radius. We know there's an error associated with our measurement. Yes, the measurement of radius is correct up to 0.01 inches. So this is the error associated with our measurement of radius. Now what we want to know is how far off our calculation of volume is going to be. How trustworthy is it? And we can go through the differential methods. And I'll come back to this problem later, but just as a sense of what this thing is about, what it's going to be used for, what it's doing, this is a great example in the engineering world and in the scientific world. Coming back though, we have this idea of marginal analysis. One area in the business world where it gets used is in marginal analysis. So if you want to know how accurate a tangent line to your cost function is to the function itself of cost, how well you can, let me say this in another way. Business people don't want to deal with an ugly looking function, right? Nobody does. You don't want to walk into your office meeting and be like, oh yeah, this function can be measured or modeled by the cosine of x plus e to the I theta, blah, 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 blah. You don't want to do that, right? Nobody does. So you might be tempted to say, well, how close is the tangent line to my function? Can I use my tangent line to model changes in my function for small changes in time? Or even for large changes in time? Maybe your function doesn't change a whole lot over time. So you go to marginal analysis and you say, well, let's compare these things. Let's look at how the tangent line changes with respect to my function itself. That is what marginal analysis is doing for you. It's a way of saying, well, I know for small changes in x, the change in, for example, revenue here, is going to be approximately equal to the differential change in revenue. So the change in your function is going to be approximately equal to the change in your tangent line. And this is the y value, right, of the two. This lets you, like I said, try and figure out how accurate these measurements are. So as one quick example, we've got the demand function. So this is price as a function of the number of units being sold. We want to use differentials to approximate the change in revenue as sales increase by 1 unit from 149 units to 150 units. All right, so this tells us right away, delta X and dx, right? So this tells us that P is equal to 400 minus X. X is equal to 149. Delta X is equal to 1. Dx is equal to 1. Now the question you should be asking yourself is, where did I get that 1 from? Well, that's just 150 minus 149, right? So the actual change in revenue is going to be delta Y, which is going to be f of x plus delta x minus f of x. So this is going to be equal to 400 minus 150 minus 400 minus 149, right? So delta Y then is going to be equal to -1. Now comparing this to dy, dy is going to be equal to -1 times dx, right? So it's dx of 400 minus x times delta x. This is equal to just -1 times dx, or negative dx. Which is equal to -1. My mistake. I made a boo-boo. I made a pretty big boo-boo. The mistake I made was reading the demand function and not reading revenue. We're given the demand function. What's the revenue compared to demand? Anybody at home know?
I'm not too sure.
So the revenue function, R, is equal to the price times the number of units sold, so X. So in this case, we're going to have, excuse me, 400X minus X squared. And this is going to change our problem pretty significantly, actually, right? Now this was my mistake. I did not read this problem entirely. I just said, oh, demand function, let's go ahead and calculate everything. No, we needed to find everything in terms of the revenue, right? The differential analysis of the revenue. Revenue, again, is demand function times X. Our demand function is P is equal to 400 minus X. So demand function is of price as a function of demand. All right, now getting to this. We have f of x here is going to be our revenue function. So we're going to have 400 times x plus delta x minus x plus delta x, that quantity squared, minus 400 times the quantity x minus x squared. We can work some of this out to get, just to reduce the actual calculation on us. Well, yeah, let's go ahead and reduce some of this. To get 400 x plus 400 delta x minus x squared plus 2x delta x, my mistake, minus 2x delta x minus delta x squared minus 400 x plus x squared. All right, we're going to kill off those two terms. We're going to kill off those two terms, right? So what we're left with is 400 delta x minus 2x delta x minus delta x squared, which is really nice for us because x is going to be 149 and delta x is just 1. So it's a lot easier to work with this equation than it would have been to work with that, right? That's convenient. At x equal to 149 and delta x equal to 1, we're going to plug everything in now and get 400 times 1 minus 2 times 149 times 1 minus 1 squared. Well, this is going to end up being 400 minus 892 minus 1, 298. Sorry, I said that backwards. Which is going to come out to be 400 minus 299, or 101, right? Okay, so that's delta 1. Which, for the sake of board space, I'm just going to store over here. This is, like I said, delta y is equal to 101. Now, what we just did was we said, all right, for small changes, or for changes in y, that's just equal to our function evaluated at x plus delta x minus our function evaluated at x. It's just a change in our y values, right? The change in our function itself. Cool. That gave us delta y. Now, we're going to compare that to dy. Again, this is for the revenue function. My mistake, I should have wrote dr, not dy. Or delta r, I mean to say. Now we've got dr. This is going to be our revenue function. So the derivative dx of r times the differential x. Okay. Our revenue function is our demand function times demand. The derivative of that thing, well, that's just 400 minus 2x times delta x. Agreed? I mean, times dx. So at x equal to 149 and dx equal to 1, dr, the differential, is equal to 400 minus 149 times 2 is 298 times 1. This is going to come out to be 400 minus 298. That's going to come out to be what, 102? So what we're saying here is that if we were to model right around 149, we were going to model our function with our tangent line. After the first new unit sold, our tangent line is going to be accurate up to $1 in revenue. dr is equal to 102. All right. So, looking at this problem, because this is a very convoluted problem, I know. And I know we are past time, so bear with me for just another few minutes. We're starting off by saying we know our demand function. We want revenue. Revenue is our demand times the demand function. Demand function is price as a function of demand. And we were told that that was 400 minus x. So multiplied by demand again, we get 400x minus x squared. Now, applying the derivative with respect to demand, we're going to get that the marginal revenue is equal to 400 minus 2x. And when we say that x is equal to 149 and the differential of x is equal to 1, the approximate change is going to be about $102. So in other words, you go over 1 unit and you're making about $102 more for that, selling that extra unit. Does that make sense what I mean? Now comparing that to our actual increase in revenue, that was $101. So the tangent line, like I said, it's accurate up to about $1, which isn't half bad. If you had changed dx to be a larger number, it would be off by more. But this gives you an idea of the accuracy, like I said. Is everybody cool with that? Folks at home, does that make sense?
Yeah.
Yeah. Awesome. Well, having said that, I will let y'all go. Again, this was week 7, page 46 that we're ending at. I'll stick around if anybody has any questions. In the meantime, have a good one, everyone.